Okay, good morning, everybody. How are you doing? Enjoying the life of pi? Have you found the tiger yet? That's me. All right. So, recall from last time, we defined the energy momentum tensor for electromagnetism. T mu nu, and it kind of came out of the blue, so let me say a few words about it. What we showed is that if you construct this quadratic quantity out of the electromagnetic field tensor, this is the energy momentum tensor, this is the electromagnetic field tensor. I'm afraid it's the same symbols. If you construct this quantity, then it obeys d mu T mu nu equals 0 using the Maxwell equations with no currents. Furthermore, this quantity is related to what people had already understood were the energy density and the energy flux in the electromagnetic field, the Poynting flux. Okay, so the relationship is that T00 is 1 over 2 mu naught E squared over C squared plus B squared, and T0I is equal to 1 over mu naught C times E cross B I. Okay, so you can check that just by calculating the components of this guy. But the key equation is this one. And this equation is in the form of what we call a conservation law. We've already seen that the electromagnetic current obeys, for current obeys this. That was a conservation law. And this energy momentum tensor likewise. And when you have such a conservation law, you have conserved one or more conserved quantities. One in this case, a whole 4-vector of conserved quantities in that case. And these are very important. So, of course, if I write out what this equation means, it means d naught t naught naught plus d I t I naught equals 0. Okay, that's writing just down this equation for nu equals naught. I've got a sum over these indices. And it means d naught of t naught I plus dj tji equals 0. So actually here I have 4 equations. This is the equation for nu being naught, the equation for nu being 1, 2, or 3. So there are 4 equations. There are 4 conservation laws. And as you might guess, what this means, when I have such equations, what I should do is write down something I'll call the energy, which is integral d3x t naught naught. Okay, and then it follows that the time derivative of the energy equals integral. I'm allowed to bring the time derivative under the integral because this is a function of t and x. I can bring the time derivative, act on the t, use that equation, and what I get is minus d3x di ti naught. This is a divergence. And then using the divergence theorem, I can write this as minus integral ti naught dsi, where this integral is sum over some volume v, and this integral is over a surface S, which bounds the volume v. And what this is telling me is that the rate of change of the energy inside the volume v is the negative of the flux of energy out of the surface S. Okay, so providing I pick my surface a long way away from the source where there's no flux traveling, then the energy will be conserved. Okay, and likewise, now, by the way, the first thing should maybe worry you about this expression. Does anything worry you about this? I'm trying to do relativity. What does something bother you about this expression? What? It's space. Yeah, I've forgotten about time. I thought relativity included space and time. This doesn't look very invariant, right? It doesn't look Lorentz invariant. But in fact it is. It's Lorentz covariant. And you can see that. So in fact, this is the zero component of a 4-vector. Okay, the effect of the d3x and the 1, 0 index is they cancel out, leaving this index the index of a 4-vector. And to see that, just notice that I can write it as, we can write it as integral t0 mu epsilon mu nu alpha beta dx nu dx alpha dx beta. Because obviously here I have, so let's do the following. So I'm going to integrate over some volume V. So I choose my volume to be any spatial volume. Okay, so this is some volume. It sits in space-time. And these dx's are the directions within that volume. Okay, so I'm picking some volume that defines, I'm picking some slice in space-time. Space-time is 4-dimensional. I pick some 3-dimensional flat slice. The directions inside that slice are spatial. And so now within a coordinate system where that slice is at constant time, this would be dx. This guy's completely antisymmetric. So if this is dx, this is dy, this is dz. And then this would be this has to be the index 0 because these are 1, 2, 3. Okay, so it's proportional to this. There's a factor of 1/6 because there are 6 permutations of these indices. But this is obviously the 0 component of a 4-vector, which is that when I make, let's put that something else, gamma, as the 0 component of a 4-vector. Oh, I said it here. Okay, of a 4-vector here. Sorry?
Has an index of wrong.
Sorry, this is equal to that when gamma equals 0.
Yeah, Okay,
Yeah.
but then that expression in the integral, shouldn't there be something contracting the gamma? I mean, it looks like it's standing out by itself.
It does stand up by itself. This is P gamma.
Okay.
Okay, and this is called the energy momentum 4-vector. Okay, so what this means, the fact I can write it this way, means that if I do carefully transform my x's and t's in this expression, I will discover that, in fact, this is the time component of a 4-vector. Okay, and the space components of the 4-vector, the space components, pi, in fact, pi c will be integral d3x T0I. Okay, so by similar argument, the spatial components of those 4 vectors, remember this T matrix is symmetric under its 2 indices. So the spatial components of that quantity are the spatial components of a 4 vector. And what we do is we write this 4 vector, P gamma, is the energy momentum 4 vector, okay, which is written like this. And this quantity is also conserved, as you can easily see. So I take the time derivative of this quantity. I bring the time derivative under the integral. I've got d naught t naught I. But from here, d naught t naught I is just minus the divergence of tij. So it's again a divergence. Again, it's just a surface term. And it will be 0 if I take the surface to be where tij is 0. These components are actually called the stress. Okay? So T naught naught is the energy density, T naught I is the momentum density, Tij is the stress. And if you want to know what is the stress, okay, we know what stress is, but stress is stuff that pushes energy, pushes momentum around. Okay? So if I want to push the blackboard around, I better apply some stress. Okay? Stress is forces. That's what stress represents. So if you ever have a situation where something is pushing something else, you have to have a Tij. That's what causes the momentum of the object being pushed to change. Right? That's what this equation is telling you. And the converse is if you don't have stress, you can't change momentum. Okay? So unfortunately, stress is a necessary aspect of motion. Stress is necessary to motion. So Tij is called the stress, the spatial stress. Spatial stress, the tensor of spatial stresses. Okay? Now, what we've seen is that that we have these 4 quantities which are conserved. I should make this a vector. I had to put the C here just for dimensional reasons, right? Because any momentum is mass times velocity in dimensions. So whereas energy is mass times velocity squared, half mv squared. So I need the C there just for the dimension. So it's put there just for the definition of P. We've seen it's conserved in electromagnetism. So let's calculate an example. An electromagnetic wave, okay, which we already studied. We'll just take a linearly polarized wave, polarized in the z direction with the moving in the x direction, electric field in the z direction, Ez of x minus ct. Ez is any function, so it's just a pulse of electric field traveling along in the x direction. And B, as we also discussed, B is 0 minus Ez over c times x minus ct, 0. So that's a plane wave solution to the Maxwell equations. And now we can calculate T naught naught. T naught naught is 1 over mu naught Ez squared over c squared. Where did I get that from? Remember, the 1 over mu naught is up there. The F involves E over C. So when you work out the relevant, in fact, it's from over there, somewhere else. There. There it is. T naught naught is E squared over C squared. And the T naught I is equal to 1 over mu naught Ez squared over c squared as well. Okay, because I just calculate E cross B. This is in the z direction, actually. 0, 3. Sorry, it's in the x direction. The only component of E cross B is this vector cross this, right? So it's the z component times the y component. And I get a minus sign. And so the flux in the x direction, T naught 1, is the same as T naught naught. And what this means is that the energy in the wave is equal to the area. Okay, there's a transverse area, which is the YZ area, right? The wave only depends on x. So there's some transverse area, which is the area in the YZ plane. Nothing depends on y and z. So the energy, so the integral dx dy dz is just the area. Okay, so this is integral dy dz times integral dx of Ez squared, the same function. It's just a function of x minus ct times epsilon naught. And the momentum is the same thing divided by c, is area integral dx Ez squared epsilon naught over c. And so from this we conclude that that the magnitude of the momentum is equal to E over c. So for an electromagnetic wave, the momentum is just E over c. So in particular, this 4 vector, P gamma, if I work out its length, its Lorentz invariant length, that means I say P gamma, P delta, eta, gamma delta. That's a Lorentz invariant quantity corresponding to the length of the vector, this 4 vector. This is equal to minus P naught squared plus P vector P squared. Now let's see, this is a little confusing. So let me write it this way. P1 squared plus P, that's still confusing. I'll just write out the answer, okay. This is minus E squared plus C squared P squared, which is equal to 0. Okay, so light waves have four vector momentum or energy momentum whose square is 0. And so the reason for doing this is just to emphasize that people knew all this before 1905. And this was a very profound clue that somehow the energy and the momentum of electromagnetic waves are related in this very strict way. And this was a clue as to what you should do with particles more generally. Of course, around the same time, 1900, Planck had postulated that light comes in packets of energy. And Einstein had elaborated this. And so it was very natural to think of a wave of light as actually being composed of a set of particles. And so this formula here, then it was natural to think of this as the formula for each individual particle of light. Okay, that came along with the quantum theory. Yeah.
You said they already knew that before 1905?
Oh, yes.
Why did they use the metric before relativity?
Oh, what they knew is the following, that the momentum carried by a light wave was its energy over c. That's all they knew. They didn't know this. Yeah, that's right. They didn't know about the metric. But these were the kind of clues which were available. Now, what you'll do in one of the exercises in the tutorials is to just use this fact to prove, and energy and momentum conservation, this is enough to prove E equals mc squared. Okay, so this plus energy and momentum conservation allows you to prove E equals mc squared. So kind of all the ingredients were really there. Now, let's move on to particles. This was electromagnetic waves, but let's move on to particles and try and see how this generalized to particles. After all, in the Maxwell equations, we have J mu. J mu is the current. The current is carried by particles. We need to understand the dynamics of these particles as well as the electromagnetic field. So particles. Okay, so what is a particle? Well, a particle is a point-like object which moves in space-time. Okay, so a particle travels in space-time along some world line. Okay, so this is Minkowski's terminology. Minkowski said the world is really space-time. It's not space, it's space and time, and they're unified. You can transform one into the other as you change coordinates. But so particles somehow live in this arena. And what is a particle? Well, at any given moment of time, it looks like a point. So as you run time forward, the location of the particle changes, and that's represented by this world line. Okay? So each one of you is following a world line. Some of your world lines started in India, and then they came over to Canada, and who knows where they will go after that, okay? But we're all following world lines in this picture. And of course, to stay young, we need to go as fast as possible. I don't want to encourage airline travel, but that's what physics tells you. What? Speeding is also a very bad idea. Okay. But it does keep you young. And unless your world line ends. Okay. Which is another possibility. Okay. Right, so a particle follows a world line. Now what is a world line? It means x mu as a function of some parameter, lambda. And lambda we use just to parameterize the world line. Okay, so So this point on the world line would be lambda equals 0. This point would be lambda equals 1. This point is lambda equals 2. Lambda is just some completely arbitrary parameter which runs along the world line. To be a good parameter, the only thing it needs to do is to go in one direction. Okay? It needs to be monotonic. So lambda needs to continuously increase as you go along the world line. Okay? But any parameter which does that is equally valid. So this is the parameter which parameterizes the world line. Now, the tangent vector, or tangent 4 vector, to the world line is dx mu d lambda, just the derivative of x, and that's obviously a vector in space-time which will point, which is parallel, which is parallel to the world line at that particular point, lambda, parameterized by lambda. What we say, some terminology, is that, having this 4 vector, we don't really care about the size of this 4 vector because lambda was arbitrary anyway. But we do care about various properties like this. You see, in an expression like this, the lambda is coming in squared. And so if I change lambda, I'm going to change this expression by the square of some function. So I'm not going to change its sign. Whatever I do, I won't change the sign of this expression. So if this expression is positive, we call this time-like world line. Okay, time-like because you'll remember, sorry, negative is time-like. You'll remember that eta naught naught is -1. So if dx is in the time direction only, this quantity is negative. So we say this is time-like if we say the tangent vector is time-like if this is negative. If it's equal to 0, we say it's null. This is like light, like a light wave. Light wave traveling at the speed of light, where dx equals c dt. Or if it's positive, we say it's space-like. Okay. Now, it's just a fact that in nature, there seem to only exist the first 2 types of particles. Okay, there are particles like us who follow a time-like world line. There are particles like photons that follow null world lines. And there are no particles which follow space-like world lines. They would be pretty interesting if they were, because they would be traveling faster than the speed of light. Okay, so these are tachyons. They move faster than light. And they do not seem to exist. Like magnetic monopoles. In principle, Maxwell's equations allows magnetic monopoles, but they don't seem to exist. Likewise, tachyons don't seem to exist. Though, yeah, we'd certainly like to find one. Now, let's focus on massive particles for time-like, with time-like world lines. These are otherwise known as massive particles. We can define a proper time. Okay, which is a Lorentz invariant quantity. And this is defined by c squared d tau squared equals c squared dt squared minus dx squared. Okay, so we take some little piece of the particle's world line, which where the tangent vector is proportional to dt, to c dt and dx. And we form this combination, which is Lorentz invariant. And by definition, it is positive because these are time-like world lines. And so we can, because it's positive, we can re-express it as the square of something. And the something is this d tau. So in other words, d tau equals dt times the square root of 1 minus v squared over c squared, where v is equal to dx dt. The velocity of the particle, the ordinary velocity, is dx dt. So for massive particles, we can define this quantity tau, and tau is then a parameter along the world line. So tau is then a unique parameterization Lorentz invariant Lorentz invariant parameterization of the world line. Tau equals integral dt root 1 minus v squared over c squared. When I say unique, it's unique up to a constant. So now we can define 4 velocity, which is a Lorentz 4 vector. This board doesn't like me. So the 4 velocity is then defined as u mu equals dx mu d tau, and this satisfies eta mu nu u mu u nu over c squared equals minus 1. Okay, which follows just from that equation. So the 4 velocity is dt d tau dx d tau, which d tau is dt, so this is 1 over root 1 minus v squared over c squared, and this component is dx dt over root 1 minus v squared over c squared. Dx dt is v, so when I calculate this quantity, I think this should be a c, ct, and this should be a c to make the dimensions correct. Okay, so, and then we define the form momentum, P mu, is equal to some number, the mass. This is called the rest mass of the particle, times u mu. That's a 4 vector, and likewise it follows that P eta mu nu P mu is equal to minus m naught squared c squared. It's a momentum squared. Now, I believe I've unfortunately changed dimensions on you. Let me just check that. U mu has velocity of has a velocity. Yes, I'm afraid I'm going to now. I call this the energy momentum 4 vector. Let me switch it to always call it the momentum 4 vector, and then define my 4 vector to be P gamma is equal to E over C and P. Okay, so this is the 4 momentum. Okay, and then what I said before was correct. So I'm going to just call this a 4 momentum for brevity, and its dimensions are those of momenta. This is a 4 velocity, and its dimensions are those of velocity. And then the energy, which is P naught is P naught C. This P naught has dimensions of momentum, so the energy is P naught C, and that is equal to square root of P squared C squared plus M naught squared C to the 4th. Okay, so when we combine energy and momentum into a 4 vector, we have to introduce the mass. The spatial parts of the 4 vector are the momentum. The time component is naturally the energy over c. And now we notice something immediately, which is that if the momentum of the particle is 0, the energy is not 0, right? The energy is, so the energy, if p equals 0, for a particle at rest, if p equals 0, then E equals m naught c squared. Okay, which is Einstein's formula, E equals mc squared. So that's a sort of totally formal derivation of E equals mc squared. But what this is telling you is that once you start putting things together, like energy and momentum, into 4 vectors, they become related. And then the mathematical machinery sort of has a logic of its own. And what the mathematical machinery points to is that actually a particle at rest has some energy. That's not a physical argument. It's a mathematical argument. But it's nevertheless a clue towards that formula. And we'll see in a moment when we do Noether's theorem, then it becomes rigorous. Then this derivation is in fact correct, because in Noether's theorem, the derivation of energy and momentum are related, and the way they emerge is in just this fashion. The velocity of a particle dx dt is equal to m naught dx d tau over m naught d by d tau of ct over c. Okay, so that's just an identity to calculate dx dt. The numerator is, of course, the 4 momentum, spatial components of the 4 momentum. The denominator is the time component of the 4 momentum over c. And so this is equal to p. The velocity is the speed of light times p over the square root of p squared plus m naught squared c squared, and you can see that the velocity, so Yes, and so it follows that the magnitude of the velocity is always less than c when m naught is non-zero. Okay, so we started off by assuming the particle was time-like, so we're just checking consistency. Furthermore, gamma, which was 1 over root 1 minus v squared over c squared, is equal to square root of p squared plus m naught squared c squared, and divided by m naught c, and this is bigger than 1. Bigger than or equal to 1, and it's equal to 1 if the momentum is 0. So for a moving particle, the energy E is gamma m naught c squared. Okay, so this expression here is just gamma m naught c squared. So how does this connect to classical mechanics? Or Newtonian mechanics? We have that the energy is m naught c squared over square root 1 minus v squared over c squared. And so if v over c is much smaller than 1, this is m naught c squared. And then I just expand the square root using this expansion. 1 minus x is 1 plus x over 2 plus order x squared. And so this is m naught c squared plus 1/2 m naught c squared times v squared over c squared plus order plus m naught c squared times order v fourth over c fourth. And so here we have 1/2 mv squared, the usual formula for kinetic energy. Okay, this is small for v much less than c, and this is a constant. So this formula for the energy is completely consistent with classical mechanics, Newtonian mechanics, in the limit of small velocities, because I neglect this correction. That's just a constant, so it doesn't affect energy conservation, and this is the usual formula for kinetic energy. Okay, so everything I've done is sufficient for you to then understand the formula E equals mc squared from a physical point of view. And I'm going to give a third derivation in a moment by using Noether's theorem, and that's the most profound derivation of all. Before we do that, I want to derive the Lorentz force. So this is the other aspect of electromagnetism, that particles moving in an electromagnetic field feel a force from that electromagnetic field. And this can very easily be derived using this Lorentz invariance and this tensor notation. So let's talk about the Lorentz force. So just to remind you, the full velocity of a massive particle is dx mu d tau. This is equal to d of ct d tau dx d tau. And we want to know how this full velocity changes in the presence of an electromagnetic field. So we want to write down some equation which is analogous to F equals ma, and we expect the particle to have some inertia, which will be this mass. So that's a free parameter. Describes how massive the particle is. This d mu d tau is the 4 acceleration. And we have to equate this to something involving the field strength tensor. Now, particles have different charges. So the one thing we know is that that force is going to be proportional to the charge. This is the charge of the particle. Let me call it little q. Okay, so it's just some number measuring the charge of the particle. And what else can I put on the right-hand side? Well, I want to put the field strength tensor. So F mu nu. And that doesn't work because the right-hand side has 2 indices. So what can I do? There's only one thing I can do. With what?
For velocity?
For velocity. That's the only thing you got left. Okay. So you want an equation. So we'll lower that index and contract it with the full velocity. Okay, that's the only thing that makes any sense. So that's the Lorentz force. And we can check this. So let's work out the I component. So if mu equals I, this reads m naught d2xi d tau squared equals q f I0 d of ct d tau, that's u0, plus q Fij uj. And what I have is that uj is equal to gamma v, okay, where v is the velocity. So v is always dx dt, okay? By definition, the velocity is the rate of change of position with respect to time in the coordinate system, but the u is dx d tau. U is dx d tau, and then of course dt and d tau are related by that formula up there, which involves the gamma. So dt is gamma d tau. So we have this formula, and Fij was just epsilon ijk bk. And so this is equal to gamma. dt d tau is gamma. Fi0 is just ei over c. So the c's cancel, and we get gamma times q times EI plus V cross B I. Okay, so just do that in detail. Epsilon I, J, K, B, K. This is V, J. I took the gamma out the front. And so this is V cross B. Now, we're still not quite finished, because let's reinterpret this side. You see, so this side is M naught times gamma, because d tau is dt over gamma, times d by dt of, write it this way, gamma d by dt of pi. Okay, because I use the fact that d tau is gamma d tau is gamma is 1 over gamma dt to turn this into a d by dt, and p is m dx d tau. Okay, so the final equation, the gammas cancel, and it's dpi d tau equals q ei plus v cross b. Let's write it as a vector, spatial vector. dp dt is E plus V cross B. Okay, so that's the correct relativistic Lorentz force. And notice that I write it here with d by dt. A force, by definition, is the rate of change of a momentum, even in relativity. Okay, and so you use the ordinary time, not the proper time, in this equation. Yes.
It doesn't, I mean, apart from the velocity, it doesn't look very relativistic. Right. And I assume the idea is that I assume the idea is that in terms of if you speed up, you change the E and the B fields, and that's where the contraction and time dilation come into it.
Oh, yes, exactly. So this doesn't look very relativistic, but notice the following. Remember this P. For a start, P is not mv. P is gamma m naught v, right? So as the particle speeds up, the gamma gets bigger and bigger and bigger. And that means it's harder, if you've got a given electric and magnetic field, it's harder to accelerate this guy. Because as it reaches the speed of light, this P is going to go to infinity. And then the rate of change of P is small compared to P. So a particle with a high gamma is like a bullet. I mean, you can't deflect it. It'll go, the higher the gamma, the harder it is to change the direction of the trajectory. The P is huge, and the dp dt is finite, and which is this side, and so you can't move it. So it really does incorporate relativity through this gamma factor.
Classical electrode.
It is. It's true for classical. What would not be true is this factor. Okay. Classical electromagnetism, they weren't aware of the gamma. That's the only thing they were not aware of. Okay. Everything else is and you can see, that's right. Okay, so now let us consider the action for particles. This is forces, but a more fundamental quantity, then forces in classical mechanics is the action. And let's now start to think about the action for particles and what the action should be in relativity. And then then these conservation laws and the equations like E equals mc squared will follow very, very naturally. So Hamilton's action principle. Okay, so this is one of the great mysteries of the world, that everything that happens in it is described by an action. We don't know why this is true, but it seems to be that every force, every force or phenomenon everyone has ever discovered in physics can be described by an action principle. It's still a great mystery why that's true, but this is a extremely powerful fact. So relativity, general relativity, the standard model of particle physics, it's a mystery which I think is still not fully understood, why all physical phenomena described by an action principle. In Newtonian mechanics, we write this action principle S as integral from some initial to some final time of 1/2 mx dot squared minus v of x, kinetic minus potential energy. And the statement is that Newton's equations F equals ma, or mx double dot, by the way, dot is d by dt. Mx double dot is minus gradient v. These are equivalent to the variation of the action being 0. So the variation of the action is 0 around classical paths, which are paths or trajectories satisfying Newton's equations. We also write this more generally as the integral of the Lagrangian of t. And later in the course, you will learn about the Lagrangian. Throughout this course, you will learn about Lagrangians. You'll learn all about the Lagrangian for the standard model, and for gravity and everything else we know. So let us now think about the Lagrangian for particles in relativity. I can keep going there, I suppose. So again, this notion of an action is another unifying principle. We're going to describe everything in terms of a single action. So when I describe a particle, you should always bear in mind that that particle is just a piece of a giant action, which is the action for everything. And if I can define the energy of a particle and the momentum of a particle in terms of its contribution to the action, then that's part of the total energy and the total momentum, which will be defined the same way. So let's consider a free particle, the simplest possible case. A free particle in Newtonian mechanics. Newtonian mechanics S equals integral dt 1/2 m x dot squared. Just the kinetic energy. In relativity, the question is, I'd like to write down the action, some kind of function of the trajectory of a particle, which when I stationarize it, when I insist that delta S is 0, gives me the right equations for the particle in relativity. And there's only one candidate for the action. Okay, so in Newtonian mechanics, a little bit arbitrary. Why did I suddenly write down kinetic energy with half mv squared? I mean, this was all inferred by Newton and Hamilton. But in relativity, we've unified space and time. It's really only one quantity which you could think about. So what is it? A particle is traveling in space and time. Okay, so x and ct. Here's the particle. That's a trajectory of the particle. If it's a massive particle, the trajectory is time-like, but otherwise it's arbitrary. What property of that world line can I consider to be something which I could vary? What's a property of this world line? The proper time. Just the length of the world line. Okay, the proper length of the world line. Proper length. Proper means this relativistic of the world, relativistic invariant length. So it's just integral d tau, which is equal to integral. So the only possible candidate is that S is proportional to this quantity. There may be a constant there. There's nothing else we can write down which depends only on the trajectory of this particle and is Lorentz invariant. And this is the square root of minus eta mu nu dx mu dx nu. Okay, so that's the squared length of an element of the world line. And I just add them all up to get the length of the world line. So this is equal to integral square root c squared dt squared minus dx squared. Now you say the first thing is I want to reproduce Newtonian mechanics in the limits where the velocity is small. We will reproduce Newton when dx dt is much less than c by taking S to be equal to minus m c squared. I'm going to put an m naught just to make sure that this is the rest mass. It's just a constant. It doesn't depend on the velocity. C squared integral dt square root 1 minus x dot squared over c squared. Okay, so this integral here, I can pull out the c and the dt. So that's dt root 1 minus x dot squared over c squared. So all I'm doing here is fixing the overall constant. And I'm fixing it by fixing the coefficient of the velocity squared to be a half. Right? Because when I expand this out, what I'm going to get is minus m naught c squared times integral dt. That's the first term. And the next term in this expansion is plus m naught plus integral dt 1/2 m naught v squared, or x dot squared. Okay, so this is Newton. And so this expression for the action will reduce to a constant piece which doesn't depend on the trajectory at all, the x of t at all, and so it doesn't affect the equations of motion, and this Newtonian piece. So we've learnt that the meaning of that constant. The constant is the mass, the Newtonian mass, and it should be included. Okay, so now we are ready to discuss Noether's theorem. So this is the action for a particle, in a free particle in space-time. It's also going to become rather clear how to include forces. We'll include forces by just modifying this action, by adding terms that depend on the electromagnetic field and other terms. And eventually we're going to modify it to include gravity. In fact, I hope we'll do that at the end of this lecture. But the starting point is this free particle action. And all we've done is we've noticed we have to include a constant here, and then we've interpreted that constant as the Newtonian mass of the particle. Now let's discuss the Noether theorem. So Emmy Noether was an absolutely remarkable person who was a young Jewish woman in Germany at the beginning of the 20th century. She was a brilliant mathematician and totally discriminated against, okay, for all reasons. She was employed at a university without pay as a lecturer. Okay, so she had to live off her parents, but because she was a woman, they didn't feel they needed to pay her. And she was kind of tolerated by the other mathematicians at their seminar, Hilbert, and she was in Göttingen, which was a famous center for physics in Germany. She was sort of tolerated by the others. They realized she was brilliant. She was actually a pure mathematician, and her biggest contributions are in pure mathematics. But she's managed to see something which Newton, Maxwell, Einstein, and all the others had missed, okay, which was the explanation for why things are conserved in nature. Why is there something called the energy? Energy is a very nebulous thing. I mean, you can't point to energy and say that's energy. It's a quantity which is a constant. In certain situations, actually, it's not constant in general, but in certain situations it's constant. And momentum, likewise, and angular momentum, and electric charge, and all these other conserved quantities. So she realized why there are conserved quantities. And her realization is actually the basis for the development of particle physics, fundamental physics, throughout the 20th century. She is often not acknowledged enough, but her contribution was absolutely fundamental. And this is her theorem. It's extremely simple, but very, very deep. The theorem says the following. For every continuous symmetry, okay, so continuous symmetry is like a rotation. It's a symmetry where there's a parameter in the symmetry which can take a continuous range of values. For any continuous symmetry of the equations of motion which are derived from an action principle, there is a corresponding conserved quantity. Okay, so a symmetry means you have a conservation law. And it's interesting, and I encourage you to look at the different proofs of Noether's theorem in many different textbooks, and you will find they're all different, and many of them, in my view, miss the point. And so I think not only was she not properly acknowledged, she was also not really properly understood. But it's a very deep and powerful argument. Yep.
Is symmetry of action equivalent to symmetry of equations of motion?
No.
Yeah.
I'll come to this in a moment. The key difference is the surface terms. So the equations of motion follow from the requirement that the variation of the action be zero under variations, any variations in between the two endpoints. And this conservation law is a local quantity. It means that sort of in between Ti and Tf, I'm going to show some quantity is conserved. D by dt of some quantity is conserved. It doesn't matter about the endpoints. So that is the distinction. So the equations of motion follow from variations independently of endpoint effects, variations for times which are not at the endpoints. We'll see that throughout the proof. You must distinguish between variations which change the endpoints and variations which only affect the system in between the endpoints. So the equations of motion are simply the statement that any variation in between the endpoints does not, the variation of the action is zero for any variation of the coordinates in between the endpoints. Okay, so a continuous symmetry is a transformation QA of t. So I've got some trajectory of the system, QA of t. These are the coordinates. Of the system. Which could be x, the position of a particle, but more generally just some numbers that parameterize a system, and the a will be just run over the number of those coordinates. And the transformation is q over t goes to qa prime of t, which is qa of t well, sorry, I wanted to just say one more thing. Transformation which for small values of its parameters. So the parameters basically tell you how big the transformation is. So for small values of its parameters, reads QA of t goes to QA prime of t. These are the coordinates. Plus epsilon AB, xb. xb can be a function of the coordinates, the velocities, and the time. We call epsilon the parameters. Okay, so, and we call xb the generators. So this is the way continuous symmetry groups always work. There's some quantity defining the manner in which the symmetry acts, and there's another quantity defining how big the symmetry transformation is. So, sorry, I've not written this right. This is QA goes to, let me write it out again, sorry. QA of t goes to QA prime of t, which equals QA of t plus this other guy. These are the coordinates. Okay, so the statement is that if there is a symmetry of a system, if I change from these coordinates QA to coordinates QA prime, the equations of motion are exactly the same. Okay, that's the definition of a symmetry. And for small values of the coordinates, this is a small transformation where these parameters epsilon AB are small. So the symmetry, in general, if you work to higher order, there would be effects involving epsilon squared and epsilon cubed and so on. But Noether's theorem is a statement which relates these infinitesimal transformations to conservation laws. Sorry?
So the symmetry or the continuous symmetry are those specific transformations?
Exactly.
That keep the equation of motion?
Yes. A symmetry means a transformation of this form which leaves the equation of motion invariant to order epsilon. Okay, to first order in epsilon. That means it's a infinitesimal symmetry which leaves a, this is a symmetry if it leaves the equation of motion invariant. Now, here's the proof. If the parameters epsilon AB are constant, we must have delta S equals 0 up to surface terms. Okay, because the statement delta S equals 0 is directly proportional to the equations of motion. Sorry, I said it wrong. Yes, the variation of delta S is proportional to the equations of motion. The equations of motion are invariant under the transformation. Up to surface terms, we must have delta S equals 0. Then the key idea is to think instead, this is the ingenious part of it, of making epsilon AB a function of time. And consider the variation, this variation, star, with epsilon AB being a function of time. This is an allowed variation. And therefore, we must have delta S equals 0 using the equations of motion. Let me say up to surface terms. Using the equations of motion. Okay, because delta S is 0 for any variation if the equation of motion is satisfied. And this gives you an identity which provides the conservation law. So let's write it out a little more explicitly. If I consider my action and substitute in this variation, so all I do is take my S, replace Q by Q prime, that by definition is S prime, plug this in, work out the first order correction to the action, first order in epsilon. The variation in the action, which is S prime minus S, this is equal to, well, it's a symmetry, so this is a quantity which must be 0 if epsilon is a constant. Okay? But epsilon is not a constant. And so the only things we can get are epsilon A dot JA. So this is something which would be 0 if epsilon was a constant. When epsilon is not constant, it's not 0. Okay, so times J of Q, Q dot T, some quantity. And we might also get quantities like this, dk dt, where k is also a function of q dot t. Okay, so it has to be of this form because it must vanish when vanish up to surface terms when epsilon A is a constant, independent of time. This one obviously vanishes if epsilon is independent of time. This one, if epsilon is independent of time, this is total divergence, so it's going to give a surface term. Okay? So these are actually the only allowable things you could get if what you have is a symmetry of the equations of motion. Yeah. Why can you have it?
Cannot. I mean, you're saying that's everything.
You can, in principle, you can, but our Lagrangian only depended on Q and Q dot. And so in my transformation, I only included Q dot, so only first derivatives. And so there's no place for higher derivatives ever to emerge. Okay, because my Lagrangian depends on Q dot, Q and Q dot. So if I think about the Q dot prime term, it's going to have epsilon dot. There's no place to get an epsilon double dot. Now, you can have an action with high derivatives. I haven't considered that. And this would then generalize. There would be epsilon double dots, triple dots, etc. Okay, good question. Now, so this is the only possibility for the variation of the action. But as we said, the variation of the action must be 0 for any variation. And if epsilon is a function of t, this is not a symmetry anymore, but it's still a good variation. Okay, so delta S must be 0. So this must be equal to 0 for all epsilon epsilon A. Yeah, I realize I should really put A, B, let me put indices here. In practice, it won't be so complicated. It doesn't have to be, yeah, that's right. Just think. Sorry, let me just. Trouble my indices. Yeah, I guess that's true. Okay, in practice, the cases we're going to consider that epsilon matrix will be diagonal, and there'll just be parameters on the diagonal. But this is the general case. So this must be 0 for all epsilon A of t if the equations of motion are satisfied. And so what we can do is just integrate by parts, and we write this as integral dt of epsilon ab of t d by dt j ab minus k ab. And that is a quantity which must be 0 for arbitrary epsilon ab of t. Okay, and if it is 0 for arbitrary epsilon ab of t, it must be that this function is 0, and so d by dt of jab minus kab equals 0, and that's our conservation law. Or conserved quantity. So this argument is extremely general and turns out to explain all of the conservation laws which we know about. Try and find some more chalk somewhere. So let's do some examples. And the example I'm going to do is this relativistic particle action. S is minus m naught c squared integral dt square root 1 minus dx dt over c squared. Hi. I guess since we're short of time and I don't want to cut into your break, let me give you the answer. And we'll go through it next time. So, translation invariance is a symmetry of the action of the equations of motion. Translation means moving in space. That just means x of t goes to x prime of t. which equals x of t plus a. This is an arbitrary constant vector. Okay, just take a particle, put it at some different coordinate. And if a is small, this is exactly of the form we required. Okay, so calculate delta S under this transformation and show that P, which is m naught, show that the conserved quantity is P, which is m naught dx, m naught gamma dx dt. Well, this one is spatial translation invariance. We also have time translation invariance. And what that means is x of t goes to x of t plus epsilon. I just shift the time by epsilon. And that's, this is so x prime of t is just the shifted version of x of t. And that's equal to x of t plus epsilon x dot of t. So in this case, we've got a non-trivial generator, which is just x dot of t. And I'm supposed to take this action and substitute and do the variation that delta x of t is epsilon x dot of t. And what I want you to show, and what we'll do next time, is that the conserved quantity derived exactly that way is P naught, which is m naught gamma c. Okay, so the beauty of Noether's theorem, it says that whatever you have in the physical world, if it's described by an action, it's part of a total action, and I want to know the energy of the whole world, of everything in it. All I do is these symmetry variations, and that gives me the total energy. If I vary the action of a particular piece of the world, I'll get its energy, or I vary it, or its momentum, or its electric charge, or anything else. It's an incredibly powerful argument, and just this fact that when we do a time translation and we work out the conserved quantity, we find this guy tells us E equals mc squared for a particle at rest. Okay, so it's a very, very, very important insight, unifying insight into physics. Are there any questions? You'll find many proofs of Noether's theorem get all involved in the Lagrangian equations of motion and blah, blah, blah. And in fact, the one on Wikipedia goes on for pages and pages and pages. And I think they've missed the point. It's really a very simple argument, but very subtle. Yeah?
If you get a discrete symmetry, then can you get a, there is
no conservation law for discrete symmetry.
Translations and a lattice.
No conservation law. Momentum is not conserved on the lattice. Yeah, that's a simple answer.
So this theorem means that we have to solve the equation for the equation of motion first, and then apply the Noether's theorem.
Yes. Well, it means Noether's theorem is a statement about some quantity being conserved when the equations of motion are satisfied. So Noether's theorem gives you a quantity. You do this variation. You calculate the j and k. It gives you this quantity. It guarantees that if I work out d by dt of this quantity and I use the equation of motion, I'm going to get 0. That's what it does. So it's a totally local statement. That's why it doesn't care about surface terms. And in fact, if you look at Polchinski's book on string theory, he gives a nice section, I think it's in book 1. He gives a nice description of Noether's theorem in the path integral. Okay? And he basically formulates it like this, but it's more general because he's doing it. He's trying to derive identities for expectations of operators under the path integral. So conservation laws give you what are called Wood identities and other identities which Green's functions satisfy. And so, but essentially, it's exactly this argument that he uses. So somehow this way of doing it is known to experts, but many, many textbooks you'll find do not do it this way. And I was a little, let me switch this off. I was a little disappointed that Z's book doesn't really, in my view, doesn't describe it. Yeah.
So this proof does not give us an explicit method for calculating the conserved quantity.
It does. It does. It says you simply do this variation in your action.
Oh, and then you match the terms.
And you just match the terms, and these are the only terms that can arise.
Okay, so
it's a constructive proof. It's just amazing, you know, and it's such a sort of trivial, in a sense, trivial argument. But bear in mind, it was missed for 300 years. So it's not trivial at all. And it drove the entire development of physics through the 20th century. Noether kind of left physics after this. She did all kinds of things in group theory and so on. She's an amazing figure. And you know, next year is 2015, so it's the centenary of Einstein and Noether. And so something I'm thinking about is we'll have a celebration of both together.